In section 4.5, we're going to start looking at the graphs of the other trig functions, namely the reciprocal ones, secant and cosecant, and then also the pair of tangent and cotangent to each other. For graphing the secant and cosecant graphs, we actually still need to draw in the sine and cosine ones, but those graphs are not going to be a part of our final answer. They're just going to guide the shape of our final answer. So do them with like a light dotted line, or do them in some way so that they don't appear to be part of your final solution. We're just using them to find the final solution. So for example, if we are asked to draw the graph of secant, then we are going to start with the graph of cosine lightly drawn in. So first, let me set up my scale. I'm going to use this fourth tick mark as 1. And for the horizontal, I'll make every other tick mark a pi/2 increment. Okay, so our regular cosine graph starts off at the point 0, 1, and then it drops down to pi/2, 0, and then 3 pi/2, -1, and back to 0. So we have the basic shape of our sine and cosine graph. And in fact, these dots might be enough for me to not even need to draw a dotted line in connecting them. But if you want, you can just kind of lightly draw something in to show what the shape looks like. So again, this is not part of our answer. I just need to know where the cosine graph is landing for me to figure out what the graph of secant of x is going to look like. So basically what happens here is, since these are reciprocal functions of each other, secant and cosine, wherever the graph of cosine hits 0, if you take the reciprocal of that, you end up with a 0 in the denominator, which means it's undefined there. So for our new answer, the secant of x graph, let me do this in a different color too, this one then is going to end up having an asymptote there. Because you can have 0 in the top of the function, but when you flip it upside down and put it in the denominator, then it becomes undefined. So wherever the sine or cosine graph touches the x-axis, those are going to end up being asymptotes. Okay, the other thing that's important to notice is think about a number that's really close to 0. Like as it's getting closer and closer to this point, the cosine graph is hitting numbers like 1/1,000,000. Well, when you take the reciprocal of that, you end up with a value that's 1,000,000/1. So what's occurring is the graph is creating a parabola, essentially, that's just touching those maximums and minimums on the sine and cosine graph. Because when the height is 1, if you take the reciprocal of that, it's still 1. But for all the other values, as you have something like a height of 1/2, it becomes 2/1. 1/1,000,000 becomes 1,000,000/1. And then the same thing happens on the negative sides as well. These create parabolas facing down because it just flips the signs. So instead of getting really close to negative 1/1,000,000, it ends up hitting -1,000,000. So it shoots down before it hits the asymptote. So once you draw in your asymptotes, wherever you see a maximum or a minimum on the graph, you're just going to draw a parabola so that it barely touches the point on either the top or the bottom of those waves. So that's our graph for the standard cosecant. And I know it's a little bit weird because it's actually like lots of separate individual pieces that are all broken up by these asymptotes, cutting them into different parts. So we actually have a bunch of tiny little parabola images on there. So what's going to be trickier is, of course, when you have transformations being applied to those secant and cosecant functions, in which case, again, just recognize which one this is the reciprocal of, which in this case will be sine. Cosecant and sine are reciprocals. So I'm going to draw the sine graph that's been stretched by a factor of 2 vertically, and that's been stretched horizontally by a factor of 2. Since this is x is being multiplied by 1/2, it's always backwards from what you expect on the horizontal motion. So that's going to be twice as long, and this is going to be twice as tall. Now, before we set up our scale, remember that in class we discussed how one of the best things you can do is find the period and then use that to make your horizontal scale. So in this case, your period is equal to 2 pi divided by b, and the number that's being multiplied by x is 1/2. So using the keep change flip rule, multiplying by the reciprocal instead, that means I have a period of 4 pi. So the rule of thumb I give you guys is it's a good idea to just take whatever your period is, in this case 4 pi, and always divide it by 4. That number doesn't change. Divide it by 4 because we're breaking it into 4 equal parts, 4 different dots basically. So in this case, I'm going to make my horizontal scale based on pi. So the second tick mark will be pi, the next one will be 2 pi, then 3 pi, then 4 pi. For my vertical scale, I'm going to make the second tick mark equal to 1 because I see that there is some vertical stretching going on in this graph, so I don't want to accidentally make it too tall and then have things end up going off of the grid here. So the second tick mark will be 1, and then 2, and then 3, and then 4, etc. So pretending that this is asking us for the sine graph being multiplied by 2 and stretched horizontally by a factor of 2, the sine graph starts at the point 0, 0, and then if you double that height, it still ends up staying at 0, 0. The next point would usually be at a height of 1, but I'm going to take that height and double it. So it's actually going to bounce up here to a height of 2 instead. The next point comes back down to 0 again, so it lands on the x-axis. And then the fourth tick mark usually hits at -1, but again, I'm taking those heights and multiplying by by 2, so I'm hitting -2. So this is the basic shape of the sine graph going through. But again, this is not part of my actual answer for what I would be turning in. So I just need to use this information so that I can see where the graph of cosecant is actually going to land. So everywhere you see the graph touching the x-axis, those are going to create the asymptotes. And that's because the reciprocal of 0 is undefined. So since the sine graph was 0, the reciprocal is 1 over 0 essentially. And then for the next part, everywhere you see a high point on the graph, one of those maximum points, draw a parabola facing up. And everywhere you see a low point or a minimum on the graph, you would draw a parabola facing down. One thing worth mentioning on this too is how do we describe the period for these? So for the period, we talked about how long it takes for the sine graph to go through one full cycle of its wave motion. In this case, one period would include both the upward facing parabola and the downward facing parabola pieces. So this has the same period length that sine and cosine do. It's still normally a length of 2 pi, but in this example, it ends up being 4 pi. That's why we stretch the scale. So that's all for the notes today. Thank you.